Hi, check it out. Isn't it beautiful? Think of beauty, joy forever. Look at this. It's a kilowatt hour meter, old school one, none of this newfangled digital rubbish. Old school analog watt hour meter that you'll find, you'll still find these in homes all over the place. This is made by Siemens, Landis & Gyr, CM100 for those playing along at home. This one has 79,000 miles on the clock, and these things are absolutely fascinating. So we're going to take a look at how these things work and do some experiments with it as well, maybe. So these things, of course, will measure the power to your house. So, of course, basically the wheel spins around in there, and then it's got a totalizer counter on here that they come around and read, and that's your meter reading, and then they subtract your previous reading, and that's what you've used since your last billing period in your last quarter or whatever. Because these things have lock-in pins on the screws here, and then a bit of wire goes through, and then a tag goes on there, so that they can tell if it's been tampered with since it last read. I suspect the reason that it's got this big oversized Perspex case on it is so that you can't just get a magnet in there and play around with them. Anyway, yep, always keep your neodymium magnet in a sock. Trust me. You'll notice, of course, this says kilowatt hours, not VA hours, because this actually measures watts. It measures true power. So it's got to, of course, multiply voltage by current to actually do that, and it's got to do it in phase as well. Because I've done a video on those energy saver scams that you get that is basically just a capacitor in a box, and it claims to reduce your energy consumption. But of course, most houses in most countries, it might vary around the world, but certainly here in Australia, you do not pay for what's called apparent power. You only pay for true power in kilowatt hours. So it doesn't matter what the power factor of the energy is you're using, you'll only pay for the real component of that. And this kilowatt hour meter is designed to measure that real component. So this one's got a couple of ports around here, which if you wanted to have your cabling come in from the side, and you'll notice that there's 3 terminals on this thing, because 2 will be the current terminal and 1 will be the neutral, or basically it's got to measure voltage. It's got to have another terminal to measure the voltage. You'll notice that these are like potted in there, so you can't attach them to here. So what I believe that's happened, the cables have gone in the back here and then go through. So once you break the seals on these, you can unscrew those and you can lift that off. And this one here, actually, that I broke off, this was actually inside here as well. It went through the plastic here somehow, so it had like a secondary protection in there, so you can't crack open the odometer and wind it back by hand.
The miles aren't coming off, going in reverse.
Well, I thought that might be a problem. Just have to crack open the odometer, roll it back by hand.
And then the lid just lifts off here, and we've just got like, it's not actually rubber, this is actually plastic. I thought that would have been rubber, but no, it's like a plastic thing. That's just for water ingress. And then this is a really nice design. I like this. It actually will pop out. Ta-da! Look at that. Beautiful, because it's got the 3 terminals on the back like this, huge big spade lugs, and they go into just the back of this. Look at this, made in Australia. Thank you very much. I really like how that's designed and manufactured. That is fantastic. So I've got the disc in here, which spins around, of course, at a rate proportional to the amount of power that's actually being drawn. It's got some markers on the sides, so just so you can see that they don't have any other benefit. This works by setting up eddy currents in this thing and a phase relationship with those, which causes it to spin at a velocity proportional to the power being consumed, and it multiplies. This is how it multiplies the voltage and the current. We'll explain that a bit more in a minute. Anyway, you can see some little holes in there. Hopefully we can experiment with that. So you can see down in here, there's one terminal down there. That's one current terminal. You can see the big, huge, thick copper go through there, and it's only going to have a couple of turns. But basically, you'll have 1 or more coils on the bottom side here actually inducing the magnetic field caused by the current. And then you'll have another coil up here, which is then also inducing current in this thing, but that's due to the voltage. And you'll see up here, there's a smaller, much thinner wire there you go. There's your voltage terminal up there. That's actually the neutral terminal, and it taps off the wire, and the other wire, the other side here, will just go down to the active side down here. So that is the voltage coil. So you've got a magnetic field produced by the voltage, but also by the current as well. And that's how they multiply inside the disc itself to actually spin it. So that's how you get voltage times current. But there's more detail to it. So if that causes the disc to spin like this, well, it could actually just keep spinning up and up in speed, and you wouldn't stop it. And that's what these little permanent magnets down here are for. There's a permanent magnet on this side, and there's a permanent magnet on that side there, and that helps retard the disc, basically add a bit of, so like magnetic friction in there, for want of a better term, to actually stop the disc just flying away. It basically keeps it at a nice constant velocity based on the amount of power being the magnetic field induced in the disc by the voltage times the current. So without those magnets, this thing would just speed off into La La Land. And then, of course, the disc just has this worm screw on it, which then just turns this reduction gear mechanism. So as you turn it like that, they slowly turn, so that it'll all be nicely calibrated to just turn the totalizer count on the front here. All right, so let's hook this up. I've got no load at the moment, so I've just got the active in and the neutral. We should measure the voltage coil like that. Yep, 880 odd ohms. That's good enough for Australia. So I've got it hooked up to one of these fan heater thingies here. So let's plug it in and see if we put a decent load on it, will it actually do anything? That's the fan. No, it's going to go very slowly. So let's put the heater on. There we go. Spinny, spin, spin. And that's on 1, heater 1. And let's make it a bit faster. Should go twice as fast. There we go. Beauty. Right, so I'm curious to know if putting a magnet near this thing can like retard it, slow it down, something like that. So I've got a hard drive neodymium magnet. So let me turn her on. No, I don't think that's good enough. Let's break out the bigger one. Wow. The interesting thing is I can feel it. 50 hertz. This is not feel-o-vision, but trust me, I can feel the 50 hertz vibration in that magnet. Wow. Yeah, I've got to be, because there's got to be energy going into this to vibrate it. So I think that is actually slowing it down. It must be. It's got to be drawing energy from it, but I can't make it stop. It's a pretty powerful neodymium magnet. I don't get the same on the side. I get it on top as well. Now, the interesting thing is, I'm not sure if you can see that. You probably can't see that moving. I'm going to set up a time-lapse camera, but that disc is slowly moving. And I've got no load on this whatsoever. What's going on? Now, you notice that I actually let that video run there, even though it had stopped. And this is a feature of this disc, is that it will actually stop itself rotating. Now, the first question is, why is it actually rotating on its own with no load whatsoever? Well, this is actually purposely designed. If we take it apart, we'll probably find another shaded coil in there, shaded pole coil in there, and this will actually give it a bit of a natural spin to overcome those magnets that we had on the other side, because those magnets, you don't get those for free. They're actually going to like drag down the disc, and then you won't get like the real power, like it'll be under-reporting the power from the customer that they're actually using. So, of course, they don't want that. So then there will be a slight steady eddy current in there that makes this thing actually turn. But why did it stop? Well, that's what these holes are. Now, let's have a look. Ta-da! There it is. There is one of those holes I talked about. There's a hole on each opposing side. Now, if we spin this around, you won't see this, but I can... It basically stops when the hole is under this magnet here. So the hole will actually stop in the position that causes the greatest reduction in eddy current in the disc. And that's going to happen, in this particular case, under the magnet here. So it's just going to stop. And of course, if you then add a little bit of extra power on top of that, like the customer actually, draws an extra 10 watts or something, will actually overcome that and slowly start creeping forward at that 10 watts. So and obviously the size of the hole and the position of it is carefully calibrated so that it's just at the point where if there's no current at all, it'll actually stop and won't rotate the disc. But any extra current on top, I don't know, there's, might be like plus minus a watt or two or something like that, then it will, the disc will start to move again. So yeah, that's an anti-creep hole. Okay, so what I've done now is physically remove that extra magnet there, and let's do the same thing again. Okay, I expect it to actually maybe go a bit faster this time, so let's give it a go. Yep, look, it's going faster. I don't even have to set up the time lapse this time. Okay, let's see what happens now with no magnet if we actually put our load on there. Will it actually just like spin faster and faster even though it's a consistent load like we had before? I'll put it where I had it before. Oh. Wait, look at that. It's spinning. This is only on fan 1. You see what happens when you don't have the magnets in there to actually to give it that sort of, retardation force in there. And if I put up the second way, whoa, it's going ballistic. So there's a delicate balance in there. Now, if we take it out, we can see what's happening here with the current coil on the bottom of the disc. And by the way, there's the voltage coil on the other side. As I said, that just connects between neutral and the active. Okay, so we have the voltage coil on the top side of the disc, we'll call it. And that induces an eddy current in the disc based on the voltage waveform. And then on the other side here, we've got 2 coils that are offset from the center. So the voltage coil is inducing an eddy current like right in the center of the disc, but then we've got 2 that are offset. And you'll notice that this one has 2 turns and this side only has 1 turn because you need these to be imbalanced so that the disc can actually rotate in a certain direction. And you need that imbalance in there for it to be able to do that. But of course, the total amount of magnetic coupling is going into the disc in here. So you're getting all of the current flowing in. It's just offset in a way that helps it turn in one direction. Because if you had current just in the center, like you did with the voltage, it wouldn't go anywhere. What I think's going on here is this part of it like this is just a way to adjust, as I said, that minimum load current there. You can go positive, negative like that, and that will just tweak that minimum load to offset the torque of the magnet. So the magnetic torque is equal to the minimum driving torque, I guess you could call it. So let's have a look at how this works in a bit more detail. We've got basically a 2-phase linear induction motor here, with one phase being the voltage coil up here, the other phase being the current coil down here. And I can take these out, and each one of these actually induces a magnetic flux into the aluminium disc down here. And the current coil does the same thing on the bottom here. So we've got both voltage and current magnetic flux fields, and they actually induce current, eddy currents, inside the aluminium disc here. And as I mentioned, the slightly offset nature of these current coils actually makes it rotate in one, or prefer to rotate in one direction like this. But of course, if we've got a perfect power factor, i.e. a power factor of 1 in our load, then our voltage and current are actually in phase. So if we're producing an in-phase magnetic flux from the voltage and current, then, well, we're not going to have any circulating air and eddy currents in there, and that's not going to produce any rotational torque in the disc at all. They're just basically going to cancel each other out, and the disc isn't really going to move anywhere. So we have to actually delay one of these by 90 degrees. So let's do some vector diagrams of what's actually happening here. Now, the current coil here, okay, if we've got current flowing through the coil, then because it's only a couple of turns, you can see in there, it's basically not inductive at all. It is resistive. And of course, a current flowing through a resistor, in this case, it's in phase with the current. So the vectors line up like this. But the voltage, check out this. I've actually cut this away and you can see that it has thousands and thousands of turns in there, just like a transformer. And when you have thousands and thousands of turns like that is hugely inductive. In fact, you want this to operate like an ideal inductor, and that's basically what it is. It's hugely inductive. And if you remember your AC basics, you might be familiar with the term civil, which is just an acronym, which a handy acronym that helps you remember whether the current lags the voltage or vice versa for both an inductor and capacitor. C stands for capacitance, L stands for inductors. So just using this acronym, if you're dealing with an inductor like we are here, then you can see that the voltage leads the current, or as they say, the current lags the voltage. It lags behind. So if you had a resistor, then the voltage and current would be totally in phase and you'd only get one waveform like this. But in a pure inductor, it's going to be 90 degrees out of phase and it's going to lag. So if this is your voltage waveform like this, then your current waveform must lag by 90 degrees. It'll be 90 degrees for a perfect inductor. It'll be less than that if it's not a perfect inductor. But in this case, we want like as close to a perfect inductor as we get in here so that it can lag by 90 degrees. So what this does in the voltage coil, or the potential coil it's also called, because it's measuring the mains voltage, then we've got a voltage vector this way, but because it's a pure inductor, the actual current is going to be at 90 degrees. And of course, it's the current that actually produces the magnetic flux. So our flux that's due to the voltage, which we'll call V flux, is at 90 degrees to the voltage. So at a power factor of 1 here, where voltage and current are in phase in your load, okay, so that's why I've got them both pointed up like this, or in phase, the actual flux produced by the voltage coil will be 90 degrees, lagging from that 90 degrees out of phase because it's an inductive voltage coil. So what you end up with here is a flux due to the current coil here that is 90 degrees out of phase to the flux caused by the voltage coil. So you will have two different phases of flux inside your aluminium plate in terms of circulating eddy currents, and that will actually produce maximum torque in the disc in the one direction, as we've talked about, at a power factor of 1. And once the power factor goes in your load goes below 1, then it becomes less optimum and you're getting less and less torque in your disc. So it's effectively measuring the true power in the load. So in terms of this being a linear induction motor, what we've basically got here is the transformer core like this. These are the stators. We've got one stator in the middle. The stator just means it stays stationary. We've got one stator leg down here. We've got the stator leg going through the core, the other stator leg over here, and we've got another part of the stator down here, and your aluminium disc in there, that is the rotor of the motor, and that's what spins around. Now, if you research these things, you might see some diagrams which show copper rings going around the outside stators and also the center stator here. And they effectively create shaded poles. So they operate just like a shaded pole motor to help the thing rotate, which effectively starts rotating in one direction. I won't go into details on shaded pole motors, but that does not seem to be the case in this particular design here. Of course, we've got the copper on the back of here, but that does not form a complete ring around the center core stator like that. This is just the lag adjust. Okay, let's see if we can kind of sort of explain this using DaveCAD and vector and waveforms and phase shift and basically like transformer inductive motor kind of action. So let's look at where the fluxes are flowing. We've got red is the flux produced by the current coil here, and we've got blue, which is the voltage flux caused by the voltage coil here. So as we've explained, the fluxes are 90 degrees apart, and any flux that's cutting through the rotor disc here, the aluminium disc, is going to create eddy currents, circulating eddy currents within that aluminium disc. And we won't care about how the currents circulate and stuff like that. We'll just look at like the transformer motor action here. Now, the eddy currents induced in this plate will be at a maximum when the magnetic flux passing through it is at a maximum. And that will be at the point that has the highest rate of change of magnetic flux. Remember, this is not voltage anymore or current. This is magnetic flux. So the highest change is when the waveform, the magnetic waveform, is at its steepest, i.e. it's changing the most amount. So we'll start at like time 0 here, and then we'll, 90 degrees. So we'll divide this up into 4 quadrants, because really there is 4 different types of action going on here, and then after that cycle, of course, it just repeats itself. So at time 0 here, the voltage flux dominates because it has the fastest, like wave shape here. Once it gets to the top, follow the blue waveform here, and you'll find that once it gets right up to the peak there's basically no magnetic flux because there's no rate of change in that. So at 90 degrees here, the voltage flux is at a minimum, but the current flux is at a maximum slope like that. So it dominates. And then as we move along, let's see if I can get this right. It comes to dominate. At 180 degrees, the voltage flux dominates again, and the magnetic flux is 0. But it's in the opposite direction. The flux is opposite when they're over here, but that produces that still produces a net torque, in a net maximum torque in the disc up here. So during the first quadrant here, what's happening is we have magnetic flux lines that look like this, and they're going down like that, and they're going through like that, and there's going to be a maximum of magnetic flux cutting through the disc like this. And you can actually look at this as like the entire plate around here, like it can flow around there as well. The details don't actually matter that much. We're just showing like the basic principle here. So during quadrant 2 here, the current flux dominates, and that is going to flow like this, and it's whichever direction, and then you'll have some flow outside of the disc here as well. So then what happens in quadrant 3? Well, there's no more magnetic flux from the current here, but voltage flux dominates. My pen's given out. Here we go. So, but it changes direction like this. Really didn't have time to build this to scale out of paint, did I? But it basically goes back in the other direction like that. So there's 4 quadrants, just repeat themselves again for the waveform. And remember, this is not the load, okay? This 90 degrees phase shift's not here due to load. This is at a power factor equal to 1, okay, which is the current and voltage are in phase in your load. This is due to the fact that the voltage coil is acting as an inductor and producing a magnetic delay, a 90-degree magnetic flux delay in there. Cool, huh? And then, as I mentioned, you can actually trim that using the lag delay just like that. You can see it's got positive and negative delay on there, and that just like offsets it. And well, we won't go into details how that actually works because it gets a bit more complicated, a bit into the black magic side of the designs of these things. But basically, this design has been around for like well over 100 years. It's like really old school stuff. Nothing's really changed. The principles are exactly the same. There might be differences in, the permeability of the materials and, all sorts of other little tweaks in the magnets and everything else. But the principle has remained the same since before all of us were born. And as I mentioned, you've got the magnet on the disc as well, which produces a matching magnetic retardation force in the opposite direction to what the disc is spinning. And we just talked briefly about a couple of the other cool aspects of these designs. Of course, you want to have practically no friction on there. Like, I just spin that up and that's going to spin for a long, long time. And that's because they will either have a jewel-based bearing in there or they'll have a magnetic-based bearing. I believe this one is jewel-based. Actually, the data sheet for this CM100, which doesn't look like this anymore, so they still call it the CM100. It's gone through several generations. It actually says either it's a double jewel or it's a magnetic levitation. But when we're talking about jewels here, we're talking about like actual ruby sapphire type jewels that are used inside a good analog watch to get incredibly low friction bearings inside the top and bottom. And of course, if you have magnetic, then you've got no contact bearing, but then it's just going to slow down due to the drag in the air and also the load on the cog in here as well. That will eventually stop it. But yeah, it's pretty impressive, isn't it? I mean, it just it keeps going forever. Now, another interesting thing is the magnet here. You'll notice that it does actually have an adjustment here. Some models will actually adjust whether the magnets actually move in or out of the disc like that. And that actually adjusts like the torque vector in there. And I don't know, all the mechanical engineers can go crazy about that. But this one is actually a fixed one which sits on there. And then it just adjusts the field with this plate here. So that's just a way to adjust the magnetic friction, so to speak, in that. But this isn't done yet in its secrets. You'll notice that it's got a bit of metal on top here and this strap. This isn't just to like hold it in place. In fact, it doesn't need this at all. What this actually does is this is temperature compensation, believe it or not, because the magnetic field will change with the temperature. So what they do is they have an inverse temperature profile magnetic material on the top here, which then changes inversely to the temperature to what the magnet does, and that cancels out the effect of temperature on the magnets. Because if these magnets actually changed, then as the temperature changed, and of course, you know, this is like outside in your box, and that could change as summer and winter, you could get like, I don't know, a 60-degree differential or something like that at the extreme ends. Yeah, that can lead to a large difference in the magnetic field. And of course, if you change that nicely calibrated magnetic torque in there, that magnetic friction, then that's going to either make it run slower or faster. And well, the power company doesn't want that. They want these things to be as accurate as possible. And that's what they're doing there. Temperature compensation. You wouldn't know it just by looking at it. Cool, huh? And on the bottom here, we've got something else interesting. This plate here, which is adjustable, F, actually, that kind of sort of gives it away. This is actually the full load adjustment. So you can actually move this plate in and out, and that will actually do like a maximum current setting, essentially. Just like we've got a minimum load current adjustment as well, you have a full load current adjustment. Cool, huh? You wouldn't, once again, you wouldn't know that just by looking at it. And what that basically does is just siphons off, once again, some of the magnetic field from in there, and that just sets you up a limit, essentially. And you'll notice the disc is full of these little dimple things, little square dimples there, and it's absolutely chocker with them. And as you can see, there's like a brushed part of it as well, just like a brushed segment, and that's on both sides of the disc, and that's got to have something to do with the circulating eddy currents in there. I can't believe they've gone to that effort on both sides of this disc just for looks, because they've already got the marks on the other side to show you that, you know, this thing actually you know, is rotating around and giving you a quantitative indications. So offhand, I can't think of how they're actually working. So if you do know, please leave it in the comments down below, and you can see the anti-creep hole there. And once again, there's some like separation around that as well. So it's all got to be very deliberate. So there you go. I hope you found that as fascinating as I did. These things are absolutely amazing, and I've never torn one down before. They're incredibly simplistic devices, but there's actually a lot of subtle engineering that goes into making these things work and making them accurate. And the accuracy of measurement on these things, because they're actually used for legal trade of electricity, essentially, just like scales have to be, you go to your local post office and they weigh something, right? That has a legal meaning because they're charging you for that weight. And in this industry, this has a term for that as well, and it's called legal metrology because, you're measuring things and you're making a legal trade based on that electricity. So they want these things to be as accurate as possible. They want them to draw as little power as possible. And there's been many refinements over the last 100 years that make these things as good as they are. And you can see there's not many parts in this at all. There's a current coil, there's a voltage coil, there's a magnetic drag thing, there's an aluminium disc for the eddy current, and there's the totalizer gear mechanism in there, and Bob's your uncle. But getting that all right is some really amazing technology. So I hope you found that useful and interesting. If you did, please give it a big thumbs up. As always, discuss down below. Catch you next time.